Today we're doing some additional practice with quadratic transformations and looking at them in different formats. So one thing that we don't get enough practice with is looking at numbers defining a function in a table. So we're starting off today with a couple of table examples. When we look at a quadratic in a table, the absolute most important thing we want to find is to look for the y values and when they switch direction. So from 2 to 1, this is decreasing. -1 to -2 is decreasing. But then it's basically switches. So it goes the other direction, and everything decreases toward this point right here. So you can also see that it's kind of like symmetric, right? The y numbers above and below are the same. So this point here is our vertex, and that is the most important thing for us to know when we're looking at a quadratic in a table. So we had f of x, and we're changing to g of x. So in the table for g of x, our vertex is still in the middle. We can tell that because we have 5, 5, and then 8, 8, right? So those are the same. So this is also our vertex. It doesn't have to be the center row of the table. It just so happens that it is for all of these ones. So we want to know what changed. Our x value of our vertex used to be -3, but now it's +1. So this went to the right by 4 units. Our y value of our vertex used to be -2, but now it's +4, meaning we went up 6 units. The next thing we need to check is whether it got reflected. So the way we do that is from 4, I'm adding to go away from my vertex, meaning it opens up. So if you think about graphing that, I have 1, 4 here, and all my other points are above that, so it's opening upward. Similarly, on this side, I'm going to erase this because I kind of want to go away from the vertex now that we know where it is. If I go from here to here or here to here, I'm adding, and here to here, I'm adding. So that opens in the same direction, because as we go away from our vertex, the numbers are still getting bigger. So there's no vertical reflection. And the last thing to check is the rate at which it's growing, to check if it's wider or narrower. So to go 1 away from my vertex, this changed by 1. And here, the same thing, to go 1 away changed by 1. So that means that it's not any wider or narrower. All that's happened is it went right 4 and up 6. So the way we would write that rule is f of x minus 4 plus 6. If we wanted to write the actual equation for this one, I don't think we're quite ready for that. So let's just think of it in terms of the transformation for right now. Second graphic or table example, if you want to try this one on your own first, feel free. So we have same thing, vertex is in the middle because we see our line of symmetry, everything above and below matches. We went from -3 to +7, so that went to the right 10 units, and -2 to 5 went up 7 units. This one, as we go away from our vertex, is growing, and here as we go away from our vertex, it's growing as well. So there's no reflection, and we can see, just like the last one, we change by 1. So to go from -2 to -1 is +1. Then from our vertex to the second point is +4. And same thing over here. 5 to 6 is 1. 5 to 9 is 4. So there's no stretch or compression. So we could write the rule for this as f of x minus 10 plus 7. All right, number 3, given the graph of f of x, find the vertex if we do f of x plus 3. So remember, this means up 3. There's no left or right because there's nothing with the x in the parentheses. So that means we just need to take our vertex, which is, assuming this is counting by ones, is 1, 2, 3, 1, 2, 3, 4, 5. So we're currently at 3, -5. If we go up 3, we'll be right here at 3, -2. So our new vertex is 3, -2. Number 4 says, if the vertex of f of x is at negative 3, 6, where is the vertex of this? So we need to understand this rule means right 6 and down 8. Then we can take the existing vertex. If we add 6 to negative 3, the new x-coordinate should be 3. If we go down 8 from 6, we end up at negative 2. Hey, that's the same vertex. Are these supposed to match? I don't know. I didn't read the instructions. There aren't any. Okay, it's the same thing. I don't know if all of these match the two things or not, but we'll keep going. If the vertex is at 3, negative 1, where is the vertex if we go left 2 and down 1? So that would be 3 left 2 would put us at 1, and negative 1 down 1 would put us at negative 2. So remember, if we're already negative and going down, that will put us even more negative. This one has a graph. We want to go 2 left and 3 up. So this is the same graph as before. We started at 3, negative 5. 1, 2, 3, 1, 2, 3. Yep. And we're going to go 2 left, 3 up. So 1, 2, 1, 2, 3 puts us right here at 1, negative 2. So yes, it is the same as the one on the left. They're matching. Cool. Number 7, compared to f of x equals x squared, that's our parent function. What changes do these vertex form equations have? So the one in common. So the thing we need to be careful of is that it's in vertex form. So here we have f of x on the left, but this one is being tricky. It has y minus 5 on the left. So we actually need to get that 5 over on the right side where it belongs and rewrite this as 2x minus 3 squared plus 5. And not worry about that version. This is the one that's in the correct form. So it says vertical compression. Well, 3 and 2 are both stretches, so we're going to not count that one. Vertical stretch, yes, they are both vertically stretched. Shifted down. This one has a minus 5 on the left and a plus 5 on the right. So they're not both down or both up. They go one up, one down. Shifted to the right. I have x minus 1 and x minus 3. Those are both to the right, and which means they're not to the left. So we have B and D as our correct answers. Number 8, we have the same kind of trick here where we have y plus 4. So we rewrite this as y equals 1/2 x plus 3 squared minus 4. Now we can compare them. So vertical stretch, this compression is supposed to be over here. So vertical stretch, no, they're not vertically stretched. They are both vertically compressed because they have a fraction that's less than 1. Shifted left, no, one of them is to the right, one of them is to the left. So they're not both left or both right. Shifted down, yes, this one's minus 5, this one's minus 4. They are both shifted down, so they're not shifted up. So as usual on this page, both sides we get B and D as the answers. I'm going to see if we want to do 9 and 10. Write an equation of the quadratic if it has a vertical stretch. Sure, we'll do these. So, or at least the one on the left. Write the equation of this quadratic. It has a vertical stretch by 2, so that would be 2 f of, moves right 2, that's x minus 2, and 4 units up, so plus 4, and is reflected over the x-axis. I like when they list reflection first, but that just means we put a negative out here with the a value. Now, remember that the transformation rule that we just wrote is almost the same thing as vertex form. We just put it as negative 2 x minus 2 squared plus 4, and throw in a y equals. So the thing that changes is we're not talking about f of x anymore. So the f goes away because it's not just it's not operating on just a function. It's being applied to a quadratic, which basically is f of x equals x squared. So we take away the f and bring in the x squared. So for the rule, we have the f, and for the transformed equation, we have the square. But we should never have both of those. If we're writing a rule, we should see an f somewhere in there, and if we're writing an equation, like a vertex form, so this is vertex form, then we should see a squared on the x term, on the x binomial if there's a shift. Okay, I'm confident this second one will have the same thing, so I'm going to skip it and move on in the interest of getting this finished. So number 11, this one has a table. Number 12 does too, so we're probably going to do both of these. So we have f of x equals x squared. What is the intent? Are we supposed to write this in the table? I'm not entirely sure. So we're going to do that. We're going to write our parent function into the table, which is 0, 0. Then at 1, we have 1 squared. At 2, we have 2 squared. Here we have negative 1 squared and negative 2 squared, and that's our parent function. Now over here we have y equals vertical stretch of 2, shifted left 4, and shifted down 6. So we'll try to apply those changes to this table. So this is not the only way to do this, but it's a way. So the way we look at this is this 2 is 2 times the y values because it's a vertical stretch. This plus 4 is going to be a minus 4 to all the x values. And this minus 6 will be a minus 6 to all the y values. So yeah, we're going to apply each of those things, and I'm just going to add on to this table and call this x2, like our new x value. I'm going to add on over here and call this one y2, which will be our new y values. So probably let's graph both of these two. Let's graph the original. We'll change this to be green. So 4, 1, 0, 1, 4. We'll graph this one in green. Our parent function goes here, then 1, 1, then 2, 4, then 3, 9. So it opens up at this width. And we'll try to oh, not great. We'll give it one more shot. Something like that. And something like that. Great. Close enough. It's terribly ugly. I know. I cannot do art, and especially not on this tablet. Okay, so we're going to look at our new values. So the x's, we're just moving 4 to the left. So these become negative 6, negative 5, negative 4, negative 3, negative 2. And our y values, we have two things. We have to multiply them by 2, and we also have to subtract 6. So I could do that as 2 separate columns for those transformations, but I'm just going to do them both at once. So 4 times 2 minus 6, that's 8 minus 6, is 2. 1 times 2 minus 6 is negative 4. 0 times 2 minus 6 is negative 6. 1 times 2 minus 6 is negative 4. And then this is our mirror image, right? So the last one should be 2. 4 times 2 is 8, minus 6 is 2. So this gives us our new points to graph, which we'll do in blue. Point 1 is let's actually start with the vertex. So negative 4, negative 6 is our new vertex. The next point we have is negative 5, negative 4, and negative 3, negative 4. And then the next point is the one that's 2 left and 4 up. So that's at negative 6, negative 2. Oh, no, this is opening twice as fast, so it's narrower. Okay, I was like, that's weird. So negative 6, positive 2. So I did this one wrong. This was negative, this was at 4. Yes. Let me fix. That's why OneNote has erasers. Okay, so we go here, and here is what the table says. So that's negative 3, negative 4 here, negative 5, negative 4 here. And then our last point we need to graph is right here. So this one is narrower. It's opening faster, or it's rising faster than the other one. And I know that's not super obvious because my drawing is so bad, but we can see that here we went 2 to the right and 8 units up, whereas on the original we went 2 to the right and 4 units up. So this one is quite a bit narrower. It just looks really, really bad. Okay, our domain for both of these is going to be all real numbers, which we can write that way, or negative infinity less than x less than infinity if you're into that. Or even if we write it in interval notation, negative infinity, comma, infinity. So lots of ways to write it. Our range should be y is greater than or equal to, and this is our transformed range, so our lowest point is negative 6. We could also write that negative 6 less than or equal to y less than infinity, or that's less than or equal, so that would be a square bracket, negative 6, comma, infinity in interval notation. All right, hopefully that gives you the idea, and I'll leave this one as practice for you to do because that took a while, and I think if you need a reference, you can go back to watch what we did on this one and apply it here. It's going to be very similar, so you can follow the same process of adding to the table, putting an x2 column and a y2 column, identifying the changes here, like this is right 4, which is, in terms of our table, the x's are +4, the y's are +5, but first we're going to multiply the y's by -4, -1/4. And funny enough, as much as I emphasized in the last video that the negative and the 1/4 are separate transformations, if we're applying it to coordinates, we do apply it together because they both are multiplying by the y value. So we'll finish this notes here. Oh, there's some more things. I think, all right, we'll do this one. All right, so number 13, list the transformations, write the equation from the graph. We should definitely look at how to do that. So we have our vertex is at 3, -4. That's important because that gives us our h and k. So this is the opposite of h, and this is k. So I know that my equation lists the transformations. So we're going to say that this went right 3. We're going to say that this went down 4. And then as we go 1 to the side, it doesn't go 1 unit up like the parent function. It goes 2 units up. So this one is vertically stretched by 2. It's not reflected because it opens up, so we have 3 changes going on here. We also have 3 changes on this one because this one has no stretch, but it does have a reflection. So this one has a vertical reflection. It has a shift left. We went from the origin to -5, so it went left 5, and it went up 6. And then if we wanted to write that into an equation, we would just use those 3 and write it in vertex form. Okay, that's where we'll stop there. These last 2 examples are the same idea with the table that we did up above. So if you want to do those, you should be able to do them on your own, and the key will be on Canvas.